Welcome again to the PyTorch Conference 2024. In this session, we'll be talking about the PyTorch Technical Deep Dive. My name is Piotr Bialecki. I'm leading the PyTorch team at NVIDIA. I'm a PyTorch core maintainer, and some of you might know me from the PyTorch discussion board. Let's kick off this talk by taking a look at a few milestones we've achieved along the way from the very early 0.1 release to the current 2.4 release. So PyTorch was designed as a simple debuggable and hackable framework. These core values, together with the dynamic nature of the framework, give users the flexibility to work on the most challenging research projects with GPU acceleration. The code felt like NumPy due to the dynamic execution and thus resulted in the simplicity we all enjoy. The timeline shows a few milestones from the past. For example, the launch of the PyTorch discussion board at the beginning of 2017, building the community foundation, allowing users to directly interact with each other, as well as PyTorch developers. My sign-up date in September the same year, just after the 0.2 release, which is also where my story starts in PyTorch. As well as the very first talk Sumit gave at the GTC 2017 describing the design patterns of PyTorch. The look back at the first year after the initial public release of PyTorch followed in January 2018. At this time, we had already over 5,000 users in the discussion board and more than 500,000 downloads of the PyTorch pip wheels. The research community started implementing the models in PyTorch, mentioning in the research papers. FastAI announced to use PyTorch in the next course, and all of it was only topped with a shout-out in the blog post to a few community members, including myself. The first PyTorch conference followed in September the same year, where PyTorch 1.0 was announced, setting the path to the first major release, which allowed me also to see a lot of you for the very first time, face-to-face. And lastly, the original PyTorch paper was also released the same year. The PyTorch 1.0 major release followed after stabilizing the APIs and introducing the first deep learning compiler backend into PyTorch. The need for a deep learning compiler was clear, as the GPUs were getting too fast, and PyTorch wasn't able to feed the workload fast enough. So Torch was also introduced as one approach to lower this launch overhead. Here on this slide, we are also seeing Torch being a subset of the Python language, allowing PyTorch to reason about the user's code and therefore speeding it up, for example, by generating fused compute kernels. Besides that, we've seen also a huge demand for model deployment work cases, and also Torch could be utilized for it, and it was able to save and export the model execution into a pure C++. One important focus of this entire development was, of course, the reduction of the launch overheads. So a lot of code in the PyTorch backend was moved from the Python side to the C++ side, allowing a faster execution. The challenge was still to keep the debuggability and hackability high while making PyTorch faster. In the same year, a lot more technological advancements were made. For example, we were able to land native AMP into PyTorch 1.6, making a lot of workloads even faster by utilizing specialized hardware units. The community engagement was then refined. The Dev Discuss board launched to discuss technical notes, the guts of PyTorch, features and future directions. And the Linux Foundation was picked as the new home for PyTorch, resulting in the creation of the PyTorch Foundation. As Sumit described in the announcement blog post, we want to continue this open source spirit for the community and especially also by the community. And thus we took the step into this direction. The usage of Torch had a few shortcomings, being a subset of the Python language. As we realized, the community likes using most or all of Python language features. So we needed a more Pythonic workflow to satisfy the PyTorch nature of being simple, debuggable, as well as hackable. We want all these benefits without the cost, and this is where deep learning compilers are still the key. So the PyTorch 2.0 launch focused on a new deep learning compiler stack accessible via torch.compile, while being 100% backward compatible. Besides that, the focus was also in this release to provide more features of model sharding approaches for workloads at scale. Now we are at PyTorch 2.4.1, and in this PyTorch conference, you will certainly learn more about the latest features and advancements of it. So in summary, let's celebrate PyTorch's birthday, highlighting the path from the left-hand side, again showing the PyTorch talk that Sumit presented for the very first time in 2017, showing the first step of a new dynamic machine learning framework. To the right-hand side of this slide, showing a GenAI-created image by MetaAI celebrating PyTorch with us. Besides all these technological advancements, of course, the community is at the core of PyTorch. So let's now talk about the enormous reach of PyTorch across research and the overall community by looking at a few statistics. So PyTorch as an AI research framework sees a massive traction among researchers with over 30,000 AI research papers published since 2023 and over 3,000 in top machine learning conferences. Seeing all these papers always fascinates me as the variety of use cases is huge, ranging from computer vision application over GenAI to even physical simulations. We are now seeing over 100,000 GitHub repositories created in 2024 alone, depending on or using PyTorch, as well as over 350,000 repositories created since 2022. But PyTorch is, of course, also used in real-world applications. So here we are seeing an example of a macro and standard cell placement for chip design using PyTorch at NVIDIA. The animation shows the cell placement during the optimization to minimize the wire length. All of these technological advancements are powered by the large amount of source code contributions to PyTorch by the community. And this year alone, we are seeing over 800 users contributed to PyTorch and over 4,000 since the beginning. The PyTorch ecosystem now contains over 100 ecosystem projects, and we welcome you to apply if you think your project, library, or tool built on top of PyTorch could benefit from the support. We have also hosted over 100 live PyTorch webinars, including Ask the Engineers, live Q&A sessions, webinars, and developer podcasts showing interesting use cases or just digging into the PyTorch internals. We are seeing over 34 million monthly downloads of the default Python pip wheel hosted on PyPI, and at this point we would also like to thank the Python Software Foundation for the support in hosting these wheels. It's an important step to start using PyTorch. Since the launch of the discussion board, we received over 400,000 posts, and we would also like to thank all users and developers spending their valuable time discussing important use cases or just helping others in solving the PyTorch use cases. I would like to also personally thank the community for their support and want to point out how welcoming and supportive we are, especially to new users. That is really fantastic to see. Keep in mind that we will host and celebrate the second Community and Contributor Awards tomorrow, so it would be great seeing you there as well. Speaking about the discussion board, I was able to dig out the very first post in the discussion board by Zemming stating how awesome PyTorch is. And I assume he was speaking for a lot of us when we first started using it. At least that was for me the case. And I furthermore also hope that a lot of you still have the same or similar feelings when using PyTorch nowadays. More and more PyTorch users are signing up in the discussion board, and I hope we can continue the fantastic discussion and support there. I would also like to encourage, especially new users, not to be shy in asking questions, and we are more than happy to help you get started. We have always done our development in the open on GitHub, but to give the community more overview about upcoming features and long-term changes to PyTorch, the PyTorch team at Meta started publishing roadmaps in the Dev Discuss board, which include this information in a more digestible form. Visit it to learn more about the future development and all new features and changes. Right now, the roadmap for the second half of 2024 is already available, so you can check it out. So we've come a long way, but of course we want to continue fostering innovation in AI research. And to kick off our look back and new developments in PyTorch, I'm now going to hand it over to Peng to talk about compiler advancements. Thank you very much.
Good morning, everyone. My name is Peng Wu. I support the PyTorch compiler team from Meta. So today I'm going to talk about compile for generative AI. Last year, the headline features for compile were mainly general capability improvements like dynamic shape, export, AOTI, NumPy. Because back then, compile was marketed as a general purpose tool. that is supposed to raise the performance floor for many. And this time we'll show you that compile can also be a powerful tool as part of a vertically optimized solution to raise the performance ceiling for a field in the fastest growing segment of ML. Today we'll focus on compile as an enabler for SOTA performance. So speaking of SOTA, a year ago, the fastest way to claim some kind of SOTA on your LLM models are probably by building bespoke LLM systems and writing custom kernels. This is because with the emergence of a single killer app, LLM, specialization becomes economical. And in many cases, specialization even becomes necessary. So that's why we saw a proliferation of single-purpose ML frameworks, especially in the LLM space. Many of them were heavily customized out of a PyTorch native experience. So that naturally makes us wonder, like, what will be the role of compile in a world of heavily specialized LLMs? So fast forward to today, I'm happy to say that compile has found its value proposition and is gaining traction in generative AI. So let me show some evidence. So today, there are more than 4,000 GitHub repos that's created over the last 12 months that are using compile. And these newer models are heavily biased towards generative AI. Flex Attention and GP-Fast has gained strong adoption in the LLM community, and both of them are based on compile. We also have compile as the SOTA performance foundation for 3 PyTorch native recipes that covers the entire lifecycle for LLM, TorchTitan, Torchtune, and TorchChat. We also bring compile to models that ML users download. So today, on Hugging Face, many of the top LLM and transformer models are compile-enabled, and many more will come. Finally, we started to see adoption of compile into production stacks, both internally and externally. We also saw compile being used to report headline tokens per second numbers. So among all the feedbacks we received from generative AI users, I particularly like this one. This is from Together.ai. They adopted compile into their LLM inference stack, inspired by GPT-Fast. Remember the question I asked earlier about why compile in the heavily specialized LLM world? I think this one is a pretty darn good answer to that question. So how do we do it? In order to make compile appealing to generative AI, we have to target a new user persona, power performance users. So those users are the ones at the bleeding edge of model performance, and they are not hesitant to do things themselves. And how do we entice them? We have to think about compiler offerings differently this time. So we follow 3 strategies. Number 1, provide a unique value that power users cannot resist. Number 2, strive for SOTA performance and demonstrate it via vertically optimized artifacts. And number 3, preserve power users' ability to customize and control. So let me give you 3 examples. The first one is flex attention. So everyone knows attention is all you need. That's in theory, but in practice, there are so many variations of attention kernels that makes it a fertile ground for writing custom kernels. And this is no more. Since the 2.5 release, we introduced the Flex Attention API, where user can specify a score mod function to customize their attention kernels. When used with compile, Torch Inductor will be able to generate highly performant Triton kernels that's specialized for each of the score mod function. This is indeed the best of both worlds. Flexibility of PyTorch meets with performance of Flash Attention. The second example is GPT-Fast. This is compile's first vertically optimized recipe. And it's also the one that changed people's perception about PyTorch native LLM performance. So GPT-Fast delivers more than 10x performance boost over the baseline version by combining compile, GPU quantization, speculative coding, and tensor parallelism. The code base is very simple. It's purely PyTorch. There's no custom kernels. It makes it very easy to understand and to modify. We also continue to evolve the repos since its initial release last November. So on the modeling side, we added support for Llama 3, Llama 3.1, Mixtral, and MOE models. On the optimization side, we added intra-node communication optimizations, flex decoding, and we reduced compile time by up to 10x. So GPFast offers really competitive tokens per second performance, especially for small batch sizes, because compile is especially good at reducing overhead. So on the first row, we show the Llama 3.1 performance on a single GPU using 8-bit quantization. On the second row, we show the single node 88100 GPU performance using tensor parallelism and sometimes combined with 8-bit quantization. And all of these performances are backed by compile. So last but not least, is an example on composability between compile and PyTorch extension points. We made a lot of quality of life improvements over the last year, but I want to highlight a few of the extension points that are often used by power users in the generative AI community. So there is user-defined Triton kernels, significant improvement on custom autograd functions, mutable custom ops, and torchbind-based custom classes. So these capabilities allow power users to use compile while still being able to customize their experiences. So to wrap up, I want you to remember this image of a giant flywheel, because it symbolizes PyTorch's systematic approach to delivering sustainable performance via torch-out compile. This is true before generative AI, and it is still true after. As for power users, we have demonstrated that compile can be a key component of your generative AI solution and can also help enable SOTA performance, while still giving you the capability to customize. So please keep in mind, every kernel that the compiler can automatically generate is one less that you have to write by yourself and maintain. So with that, the rest of the keynote will dive deep into 3 PyTorch native LLM recipes that covers the entire lifecycle of LLM development. And we'll start with the beginning of that journey. I'll pass it on to Will to talk about Torch Titan and PyTorch distributed technology.
Hi, everybody. Thanks, Peng. My name's Will, and I'm on the PyTorch distributed team at Meta. Today, I'm going to talk about how PyTorch distributed APIs helps you scale up large language models more and more easily. So I don't have to tell most of you that large language models have been large and are getting larger and larger by the day, but the clusters we're training them on are getting larger too. And as we add more and more GPUs, it's expensive and uses lots of energy, and we want to make sure it's efficient. If we just used a simple data parallel technique to scale our models, we'd run into communication bottlenecks, and training wouldn't actually get faster. So to train these models, we end up using multiple dimensions of parallelism together. Not only that, but these models come in different sizes. For instance, the Llama team at Meta released 3 different versions of Llama 3.1. The smaller 7B model that's useful in more resource-constrained environments. And the most model accuracy comes from the 405B model, but a lot of products prefer sort of a sweet spot in between. So the model code needs to not only comprehend 3 dimensions of more dimensions of parallelism, but also this needs to be flexible so that you can disable or reconfigure each parallelism for different scales of the model. And this can lead to model code that's complicated by if and else branches and duplicate copies of some of the code, making it difficult to read and maintain. So we want to help here, and we want to make it easier to write the model cleanly and still apply all these techniques. I want to touch back to something Piotr mentioned. PyTorch is known for being simple and being hackable and debuggable. And part of the reason for that is that we try really hard when we're building new PyTorch APIs to avoid adding unnecessary dependencies and to use fewer layers of abstraction, all in the name of transparency. So as a user, you can understand what the APIs are going to do and how they're going to interact. And this makes it easier for you to build new things on top of PyTorch. And when you're building new things, it might be easier to try to just code it directly up into your model. But this can, when you're building multiple different features that interact with each other, it can be more complicated to just code them up in the model. It can be worth the investment to actually build modular APIs that fit together like Lego bricks that you can take apart and reconnect in different configurations. And the PyTorch distributed team is very much inspired by these principles, and we've built a bunch of APIs for different distributed techniques that you can compose together. We want to showcase this. So what better way to do that than to apply all these techniques to a popular model like Llama? And earlier this year, we released Torchtune, which is essentially a clean room implementation of a Llama model, focusing on keeping the model code as clean and readable as possible, while still supporting multiple dimensions of parallelism and other techniques like torch compile, float8, activation checkpointing, and others. This serves as a recipe for users that want to get started with distributed training and a best practices guide. But in building Torchtune, it also helped our team find opportunities to improve our user experience and composability of these APIs and build a better product. And so far, we've gotten great feedback from users on Twitter or X, and found out a startup company, Black Forest Labs, used Torchtune to build their new stable diffusion model called Flux, and were kind enough to generate this picture for us. So now I want to dive deeper into the different features that are highlighted in Torchtune by taking you on a scaling journey, starting off with a small Llama model, and then building it up larger and larger using different techniques. So which training technique would you use first? A lot of you are probably familiar with data parallelism. Because it's a very general technique, you can apply it to many different kinds of models. And PyTorch's FSDP is also very popular. It's a version of data parallelism that also helps you fit bigger models that wouldn't fit in a single GPU. So it's a great choice to use as a first or only dimension of parallelism, and scales to hundreds of GPUs pretty easily. This year, we're excited to release a major revision of FSDP, version 2, that not only composes more easily with other parallelisms and checkpointing, but it's more memory efficient, so you can fit bigger models into the same cluster. And if you're training with float8, FSDP will also do the communications for you in float8, making communications faster as well. Together with torch compile, you can get up to a 50% speed up over a bfloat16 baseline with a similar loss curve, basically a free speed up. So definitely worth checking out if you haven't already. But we want to scale up beyond where we can go with just data parallelism. So next, let's add tensor parallelism. Tensor parallelism works by parallelizing the activations of the model. So it's inherently a little bit more model specific. And you could code it up directly in your model's forward pass and write a custom backward function for your model that expresses the communications in backwards. But this brings in some of that complexity I was talking about that we wanted to avoid. So that's what dtensor is for. It's an abstraction that lets you keep your model code simple and clean the way you would have written it for a single GPU, and then express sharding annotations that say how you want your parameters to be sharded and the inputs and outputs of your model to be handled. And dtensor takes care of the communication for you at runtime. Torchtune offers a recipe for using dtensor to get state-of-the-art tensor and sequence parallelism in a LLM model like Llama. But that's not the only thing you can do with dtensor. It's designed to be a building block that you can use to try new techniques. For example, Databricks built a new mixture of experts model called megablocks that uses dtensor to express their expert parallel sharding. And because they use dtensor, it composes easily with FSDP and distributed checkpointing. But we want to scale up even bigger, so let's go to 3 dimensions now by adding pipeline parallelism. Pipeline parallelism works by splitting your model layer by layer and partitioning your data batch into smaller micro batches, using a pipeline schedule to overlap compute for one micro batch with communications for earlier micro batches. We've released a new set of Torch pipelining APIs that makes applying pipeline parallelism to your model easier. You might want to try out the new zero bubble schedule, which splits the backwards pass into an input gradient that you can compute earlier to unblock the next pipeline stage, and a weight gradient that can be delayed to fill in bubbles in the pipeline. But to do this, you have to have a way to split your backwards pass apart. And it's a pain to actually do this manually by writing out your backward function and then partitioning it manually. So we've extended Torch AutoGrad to work together with pipelining so that you only have to provide the forward pass for your model, and AutoGrad will split the graph of backwards for you. We've also made it easier to prototype and experiment with new pipeline schedules by building a new pipeline runtime that takes a pipeline schedule as an input. So now you only have to generate your pipeline schedule as a declarative list of compute actions, like compute the forward pass for this microbatch, compute the backwards pass for that microbatch, and let the pipelining runtime deal with scheduling the send and receive communications so that they overlap well and your pipeline runs effectively. So now you've got 3 dimensions of parallelism, and you should be able to scale confidently to 2,000 or more GPUs. But at some point, you're going to start running into different problems. Individual hardware devices and network devices might not fail very often on their own. But as you scale up and up, it becomes almost a certainty that you're going to experience a failure somewhere in your system that will cause your entire job to crash and need to restart. And so as job restarts become more and more frequent at scale, we have to restart the job, and startup time and checkpoint loading time becomes critical. But unfortunately, startup time actually gets slower with scale instead of faster. So if we don't do something about this, adding more GPUs will actually end up slowing down training. That's why this year we've invested in some of the infrastructural components of PyTorch, as well as the parallelism APIs. For example, to help with job startup time, we've rewritten the TCP store server so that the process rendezvous, which used to take around a half an hour at 64,000 GPU scale, now takes around a minute. And in a collaboration with IBM Research, we developed a new asynchronous checkpointing API. So you can take, with a few lines of code change in your train loop, you can put the checkpoint save into a background thread and let your training process run faster, as well as saving checkpoints more frequently. With these fixes, you can now run at even larger scales, and this takes us to the end of our pre-training journey. These techniques will all help you pre-train a large language model for a general purpose. But chances are you'll want to fine-tune it for a more specific use case. So to talk more about fine-tuning with PyTorch, it's my pleasure to introduce Kartikay Khandelwal.
Thanks, Will. Hi, everyone. I'm Kartikay. I'm a software engineer in the PyTorch team at Meta. It's an absolute pleasure to be here today. So you have a pre-trained model, which was trained on the beefiest hardware using these large data sets, carefully crafted scaling laws, and the awesome parallelism and optimization techniques that Will was just talking about. What do you do next? Chances are that you'd want to take this general purpose model and maximize its performance on the domains and the tasks that you care about. And that's where fine-tuning comes in. Today, I'll be talking a bit about the work that we've been doing to make fine-tuning more accessible in the PyTorch ecosystem using Torchtune. Like Torch Titan, Torchtune is built using PyTorch's design philosophy, and we prioritize simplifying the overall developer and authoring experience. Late last year, we had the opportunity to talk to really interesting power users, experts, and influencers from the community. And apart from highlighting some gaps in the existing solutions, 3 considerations came up as being the most important for users. Users want to be able to customize every aspect of the fine-tuning pipeline, from data sets and prompt templates all the way to the model architecture, including making decisions such as which part of the model should be frozen, as in LoRa, which part should be quantized, as in QLoRa. Unlike pre-training, which happens on these massive, fully optimized clusters with thousands of GPUs, most fine-tuning users have anywhere between 1 to 8 GPUs with very limited VRAM. On an informal poll on one of the more popular Discord channels where a lot of the fine-tuning community hangs out, more than 60% of the users mentioned that they have 40 GB or less when they're fine-tuning. Unblocking tuning on these commodity GPUs can significantly improve accessibility of these models. And finally, users want to be able to leverage the latest state-of-the-art capabilities as soon as these are available. Your model can understand images, tell me how I can fine-tune on my own data sets. Your model can make calls to an external API, tell me how I can improve performance on the set of tools that I care about. And so while building Torchtune, we've thought deeply about each of these considerations. We've built Torchtune for a wide spectrum of users. We expose configs with meaningful defaults for each model and recipe, making it easy for beginners to get started with fine-tuning your favorite model. Each recipe follows a loose structure, less than 1,000 lines of code and a single file, making it easy for advanced users to clone, modify, and try out your crazy research ideas. We explicitly prohibit any form of implementation inheritance within the code base and treat each core dependency as an added cost for the user, which needs to be justified. Secondly, we've prioritized memory efficiency and performance improvements by integrating some of the techniques that Peng was just talking about. Our benchmarks show that Torchtune is competitive with other libraries in the ecosystem, which specialize on any one of these axes, but we do so without compromising on the overall authoring experience. I'll talk a lot more about memory and performance in just a bit. And finally, we've been working on enabling some of the latest modeling techniques. Multimodal LLMs for a wide range of architectures and modalities, support for techniques that improve model quality in resource-constrained environments, and support for building agents like function calling and tool support. But it's not just modeling techniques. Our goal is to minimize the time it takes to integrate the latest and greatest features from across PyTorch, often by working directly with the feature developers. We hope that Torchtune recipes can provide real-world examples for how different APIs from PyTorch compose with each other and over time become references for other code bases and use cases. And so these considerations around flexibility, accessibility, and enabling state-of-the-art capabilities govern not just our design principles, but how we think about priorities and trade-offs. With the guiding principles out of the way, let's take a closer look at how Torchtune is organized. Torchtune is a native PyTorch library. No training frameworks, minimal core dependencies. We expose a set of modular building blocks and composable utilities that you can use right out of the box without having to understand the internals of the library and can embed them into your own code base and your own workflows, just like you do with any NN module in PyTorch. Where possible, we try to reuse functionality from existing libraries. So this includes quantization APIs from Torch.io, image preprocessing from Torch Vision, and so on. We've built out interoperability with other libraries and frameworks in the ecosystem. So this includes Hugging Face Hub for model checkpoints and data sets, Eleuther AI's LM eval harness for evaluation, weights and biases for logging, and so on. Recipes is where all of this comes together, and we expose functionality for full model training, parameter-efficient fine-tuning, and reward modeling. Users interact with these recipes through our config system, which is inspired by Hydra. And we expose tools which make it easy for you to launch your configs on single and multi-GPU environments. We take testing and correctness very seriously. We have a comprehensive suite of unit, integration, and regression tests, and we verify correctness through numerical parity with reference implementations from the original authors before any model lands within the repo. So where are we in the library's evolution? Since our alpha release in April, the team's pretty much been heads down introducing a number of code improvements. We've added support for newer fine-tuning techniques like Dora, support for larger language models like Llama 405B through integration with FSDP2, performance improvements through integration with Torch compile and flex attention and techniques like sample packing, support for quantization-aware training, multimodal LLMs, and a lot more. The community's reception has been very kind as well. We've gotten tremendous feedback, even on areas we need to improve upon, but we've gotten meaningful contributions across the stack, including models such as Qwen2 from the original authors, and detailed recipes and tutorials for reward modeling techniques like DPO and PPO. We've also built out tighter collaborations and integrations with other libraries like the ones I was talking about before. So we've collaborated with Eleuther AI on stronger support for evaluating multimodal LLMs, and with Hugging Face on tightly integrating Torchtune checkpoints with their libraries. Let's take a closer look at how the library's design can help you optimize your own fine-tuning setup. Our goal with respect to memory efficiency and performance is to be the state of the art, or close to it, but do so without compromising on the overall flexibility, hackability, and extensibility of the library. But these can often be at odds with each other. So for example, you can choose to reduce your memory consumption by recomputing the activations in the backward pass instead of storing them in memory, but you do so at the cost of training speed. Now, if you're in the small batch size, small sequence length regime, chances are that this sort of activation checkpointing is not really going to give you the bang for your buck that you were hoping for. You'll need to try some other things like quantizing your model weights, but this comes at the cost of model quality. The truth is, when you're thinking about optimizing your fine-tuning setup, there are just numerous trade-offs that you need to think through. We believe that users are best empowered to make these trade-offs for themselves, and it's our job to make it easy for them to reason through these considerations by exposing as many levers as we can. Let's take a look at a specific example and walk through the techniques that can help you improve memory efficiency. For the baseline, I'm going to talk about the Llama 3 8B model, trained using LoRa with a fixed batch size, fixed sequence length on an 80 GB A100. This graph is going to capture the memory footprint seen during training. Now, we'll build this up step by step by composing techniques that can ultimately get you training under 24 gigs of memory. Unsurprisingly, the baseline model ooms, and I'll let you convince yourself why that's expected. Enabling activation checkpointing helps, but we still run into ooms. Quantizing the model weights finally does the trick and gets us going. What to try next, though, will not be obvious until you stare at traces produced by the memory profiler. And if you stare hard enough, what you're going to see is that there's a huge peak at the input of the cross-entropy loss, and by chunking this tensor on the sequence dimension, you can reduce the memory consumption. Compiling the model and the loss can further help you fuse operations that can make it redundant to materialize upcasted tensors, and finally get you training under the 40 gig number that most of our users were talking about. By offloading the inputs to the CPU, which are needed to recompute the activations, you can train under 24 gigs. Actually, by adding a few more bells and whistles, you can train under 16 gigs, which is nice because you can now train on a free Colab notebook. We'll be publishing some detailed examples and tutorials on how to set this up in a couple of weeks. One thing to note, though, is that low-precision optimizers like 8-bit Atom don't really help in the case of LoRa, which makes sense because the percentage of trainable parameters is so small. But the story is very different for full fine-tuning, where you do need to think about gradients and optimizer states. And low-precision optimizers can really be critical, but you do need to shard the model across 2 GPUs to train under 24 gigs of memory. What about performance? I did mention that this can often come at the cost of memory efficiency. This graph shows tokens per second on the y-axis seen during training. As expected, torch.compile can give you a nice boost in training speed, and by compiling the model layer by layer, we were able to reduce the compilation overhead down to a few seconds. Sharding the model introduces some communication overhead, which you need to pay attention to, and naive offloading to CPU, while that can give you a good memory boost or efficiency wins, is going to significantly slow down training speed. Torch compile, though, is not the only lever you can pull to improve training speed. Sample packing, where you pack multiple samples into a single instance to make more efficient use of the larger context windows that more recent LLMs are shipping with, can often give you pretty nice wins, often up to 2x. Flex attention can further improve these to anywhere between 40 to 70%, depending on your pack size. The point I'm trying to make is that by sensibly composing all of these techniques together, you can maximize your training speed while still finding the sweet spot with respect to memory consumption. Fortunately, all of these techniques are exposed as simple flags in our configs and as composable utilities in our recipes. I hope this deep dive convinced you that there's no one-size-fits-all solution when it comes to optimizing your fine-tuning setup. You just need to think through so many trade-offs, and all of these depend on like model size, data sets, the hardware that you're using, and so on. Making it easy to reason through these trade-offs required us to think very deeply about the design of the library, and that's something we hope that comes across when you use it. It's early days, but our primary hope is that we can keep pushing on capabilities, adding more efficiency wins, but do so, like I said, without compromising on the overall developer experience. If you do try Torchtune, we'd love your feedback, and of course, we'd love your contributions. If you want to learn more, do check out Evan Smothers' talk later today at the Fine Tuning Summit. All right, now that you have a pre-trained model, Martin's going to talk about how you can run inference efficiently across a range of hardware using PyTorch. Thank you.
Thank you, Kartikay. I'm Martin Yuan, a tech lead manager at the Meta PyTorch team. So we covered pre-training and fine-tuning. Now you have the fine-tuned LLM model. How can you deploy it to your applications? Just because your fine-tuned model has SOTA capabilities, it does not mean that adoption will come. Deployment matters. There is a big variety of target devices, like the servers, desktop laptops, mobile phones, AR/VR devices. Currently, the deployment frameworks of LLM are fragmented. There are a number of roadblocks in this journey, including multiple hardware-software environments, multiple components and dependencies, and it's hard to keep the consistency between the training and deployment in the LLM lifecycle. It's hard to debug on devices. How can we remove those roadblocks and easily deploy LLM to different devices? To demonstrate how to deploy LLMs in the PyTorch ecosystem, we recently launched TorchChat, a PyTorch library showcasing how to seamlessly and performantly run LLMs across laptops, desktops, and mobile phones. With this single command line in your terminal, you can chat locally with Llama 3.1 model. How can TorchChat and PyTorch help users to easily deploy their LLMs to different applications? Let's dig a little deeper into the technologies under the hood. We split this diagram environment with and without Python. So on the left-hand side of the diagram with Python, we can run the eager mode directly, or Peng just covered the torch.compile to improve the performance. Let's focus on the right-hand side with no Python, and we start from torch.export. In some cases, it's a common pain point in the deployment. The problem is when you get the entire trained model, it has a lot of dependencies that cannot be deployed. Our one approach is to completely rewrite for inference, which introduces challenges around keeping the training and inference in sync. Another approach is to use a tool that natively understands the PyTorch model code to extract via tracing the necessary compute for the inference. We call this torch.export. After this single step, most of the dependencies are gone. We also tackle other deployment challenges in torch.export. Dynamism is another challenge in deployment. Torch.export has dynamic shape support. It's expressive, and we support automatic dynamic shapes. It also has strong support for dynamic control flow with a comprehensive control flow library for if-else and loops. Now, just for fewer dependencies and support dynamism. Essentially, torch.export creates a clean separation between the model authoring and deploying that can help the downstream deployment process like AOT inductor and execute torch. Let's go to AOT inductor on servers and desktops. AOT inductor can further remove dependencies from deployment. Leveraging torch inductor in torch.compile, the compilation and the optimization can be done ahead of time. Shell libraries are generated without any Python dependency. Those libraries are accessible on servers, laptops, and desktops. To ease this journey, AOT inductor provides entry points to integrate user-defined threading kernels, custom mobs with ABI compatibility. Now, let's move to the edge devices. With privacy, latency, and connectivity restrictions, there is a strong need to have LLM inference running directly on edge devices. Wearables like smart glasses are also great form factors to capture multimodal inputs like videos, audios, and images. XLTorch is a PyTorch platform to run PyTorch programs on edge devices, including AR/VR devices, iOS and Android phones, and many others. How does XLTorch help deploy LLMs to edge devices? To fit LLM into edge devices and make it performant, there are a number of necessary steps like quantization, export, lower to hardware backends, optimization, serialization, etc. We have those parts composable with a vertical stack in TorChat and have one-line examples to automate this process. It's an industry challenge of on-device LLM debugging. The on-device behaviors may not be fully simulated on server, like the speed and the numerical calculations. We provide XLTorch developer tools to help on-device debugging. We provide implementations in XLTorch extension LLM where power users can hack the code and customize their own on-device deployment flow. If you are interested in an on-device LLM, visit our PyTorch demo booth and check out the live demos of Llama and Lava models running on Android and iOS phones. Coming back to the diagram, TorchEdge showcases the deployment technologies just mentioned above. Now, let's go in depth with a couple of challenges and how PyTorch helps to tackle them. One challenge is the variety of deployment hardware. It's likely that users train their models in one device, but deploy it in totally different hardware and software environments. The hardware variety expands across devices, and inside a single device, like CPUs, GPUs, and NPUs. We provide easy-to-use entry points and automation process for specific hardware. To further streamline this process, we partner with hardware vendors like AMD, Apple, ARM, Intel, MediaTek, NVIDIA, Qualcomm, etc., to integrate PyTorch into their own deployment flow. Second challenge, LLMs are large with billions of parameters. Running these large models in low precision helps improve throughput and reduce memory overhead. In fact, in some edge accelerators, running them in integers are a requirement. In order to make quantization easy to use, we built this PyTorch native library called TorchAO, which provide one-line APIs to quantize your model to different bit widths like int4, int8, float8, etc. Using TorchAO, you can quantize your model in PyTorch and then run it via eager, torch.compile, export, AOT inductor, and xx.torch. Visit our GitHub repo to learn more. Coming back to the first slide on adoption, we believe that an ecosystem with easy and efficient deployment solutions are critical to an LLM framework and its adoption. So in this keynote, we discuss PyTorch's enormous reach across research, community, and production. We discussed the compiler as the enabling technology for power users. We went over how PyTorch helps developers at every stage of the LLM lifecycle across pre-training, fine-tuning, and deployment. Thank you, everyone, for attending this talk. And we are looking forward to an amazing conference where we will discuss those topics and many others in depth. Thank you very much.